Good afternoon. We are visiting here at the Big Science Forum 2018 at the booth for Fusion for Energy, which is the European section of the coalition that's going to build the ITER project. And I have with me the head of communications, Stavros Hatzipanagiotou, who has very gratefully accepted to answer some questions about the whole idea. So I understand that ITER is Latin for the way. So what is it the way to? What is the goals of ITER?
Well, I mean, ITER is the way to, we hope that ITER is the way to fusion energy, that is to making fusion energy a reality. ITER is an experiment to which we have 7 international parties participating. We have more than 50% of the world's population in this project and more than 80% of the world GDP. So you should know that in ITER we have the United States, we have Europe, we have Russia, China, Japan, South Korea and India. So we have 7 of the biggest and most industrialized countries in the world. And why are they all here together? Because they all need energy. And we think that fusion is energy that we will need. We need now, but it would have been good to have it, but we don't. But it's an energy that we all think that can solve the world's energy problems in the future.
And can you elaborate a little bit more for our viewers? What is fusion and what is the importance of fusion?
Well, first of all, fusion is the energy of the stars and the sun and the stars. So it's an energy that is very well known in the universe. It's the energy that actually, thanks to which we're here, because without the sun, without the energy coming from the sun, we simply wouldn't be here. From the, let's say, physics point of view, it's when we have 2 atoms of hydrogen getting together, generating an atom of helium, and at the same time a lot of energy. And it's this energy that we would like to harness, we would like to be able to use for our own needs. This happens on the sun and the stars because the gravity, because of the big mass of the star, it will have an amazing gravity, which makes these atoms get together and fuse. On Earth, we don't have this gravity, so we are using very, very high temperatures, arriving at 150 million degrees Celsius, in order to make these little atoms get together and fuse, and of course generate the energy that comes from that reaction.
Even temperatures hotter than the sun?
The temperatures that we use here on Earth are much higher than the core of the sun, and this is, like I said, to compensate of the absence of the of gravity of the mass of Earth, which is much smaller than the sun. We have done this. This is possible. There are many fusion reactors around the world operating, so we know this is possible. We're now moving to the next step, which is ITER, which is it's a much bigger reactor, and we hope for the first time to be able to extract 10 times more energy than what we put in. So this is the main objective of ITER, to demonstrate once again that all the technologies are there and they work in order to generate the energy from fusion.
Because the experimental reactors so far have not produced a net energy gain.
Yes, this is not a failure, if you want. This was simply not their objective. Fusion is a very complicated thing to get done, so one would need to have several experiments dealing with different areas of fusion in order to be able to get there. So in the previous experiments, we wanted to make sure that the magnets that keep the plasma, confine the plasma together, worked. In other cases, simply to be able to heat the plasma at such high temperature. So there are many different experiments around the world working on different aspects. And now we think we can bring all this together with ITER to ensure that we arrive at, to produce 10 times more, which then will lead us into the next generation, which we hope would be the final one before reaching the market.
So this this is an experiment. First of all, we have to tell our readers, our viewers, that this site is in southern France and it's being built now. It's not operating at this moment. And the idea is also to, as you say, to test both the science and the technology and the materials as a step in the way to getting commercial energy. That this ITER project will not produce energy, but is a scientific prerequisite for actual commercial fusion.
Although our objective, and we have every sign to feel very confident about it, is to produce 10 times more energy than what we put into the reactor to be able to heat the plasma. The ITER will not be connected to the grid. It's not part of the experiment, and we're not interested in that at this stage. The next generation, which is called DEMO, then will be connected to the grid and will be able to produce net energy to be used by consumers. Now, ITER is well advanced in the construction. We have reached the 50% symbolic milestone last December, in December 2017, and we're moving ahead with the manufacturing of components and all the works on the site. And we feel confident that as an international collaboration, we'll be able to make it. We have set the date for the first plasma, which is December 2025. And like I said, we have all confidence that we will make that date.
And along the lines of the question of producing 10 times more energy put in, and you prefaced it before by saying that this is in the actual chamber that we're speaking about, 10 to 1. But there, on your homepage, there's an idea that is called a burning plasma that will help the reaction to be sustainable and to can you explain what the idea of a burning plasma is?
Well, I mean, I'm not a physicist, so I hope I will be able to explain it well. But theoretically, once you've reached a certain temperature and then fusion starts going, it generates heat that makes fusion continue to grow. So it becomes self-sustainable, and you only need to put occasionally a bit more energy to keep it going. If we reach this state of burning plasma, which is also called the steady state, then I think we would have reached a very important milestone, which will guide us for the future generation of reactors.
Because the whole idea of getting more energy out than you put in is helped by the fact that the plasma itself will help to create heat when it starts, that you have external heating elements, but then the plasma itself generates the heat to bring it up to the level which can sustain
absolutely,
the fusion.
and this is part of the ITER experiment. One thing that I need to underline is that here in fusion, size does matter. So as the reactors get bigger, you have a better possibility to reach this burning plasma. Mm-hmm. It's a bit like a teapot, you know. A teapot maintains the temperature of the tea a longer period than just a single glass of tea. So this is here exactly the same thing. You need to make a bigger reactor to be able to keep the temperature and sustain it as much as possible. So that's why ITER is much bigger than all the previous reactors, and that's why DEMO will also be much bigger than ITER once we get there. Is
DEMO part of the success of the successor of the ITER program, or is it a different program?
Demo is part of the European fusion program. So its party has its own, let's say, policy and its own roadmap to how to get fusion to become a reality. We're all working together for ITER. We're all going to get, we share all the results of the experiments, and we're all going to have the same knowledge. And then each party, it will go its own way of building its own demonstration or industrial reactor. In Europe, we call it demo. And we think that we should be able to start designing demo after the first experiments of ITER. Probably in the beginning of the 30s, we will have a stable design which should allow us to start thinking of how to build it. Mm-hmm. Our idea is that fusion is a reality commercially by the end, or let's say by the second part of this century. So from 2050 onwards. Mm-hmm. That's at least the European objective, the European roadmap.
Now, if we can talk a little bit about also the main idea of this conference, which is the interface between big science and industry. And in our publications, and the founder of our magazine, Lyndon LaRouche, speaks about this as a science driver, mm-hmm. that you have basic science, which provides then a jumping off point for developing industry. So what type of industries are involved, and how will big science in this ITER project generate economic growth?
Yeah. First of all, we need to say that we fully depend on industry. We cannot build ITER, we cannot make fusion a reality without industry. Now, industry, they usually have a short horizon where they see benefits coming in. In a project like fusion, where you build ITER today and then for another 20 years you may not build another fusion reactor, industry may, or some industries, may be very hesitant to get involved. By putting all these big science organizations together, what we're telling industry is that there's a steady market in this area. And now you think, well, what does ITER or fusion have to do with CERN or the other big organizations? Well, they do, because most of the components, most of the technologies involved in the manufacturing of the components are identical. We're talking about accelerators, we're talking about some nuclear technology, we're talking about diagnostic systems, control systems, we're talking about cryogenics, we're talking about vacuum chambers, or even superconducting magnets, and we all use them. Therefore, it's very good for industry to also be able to come to one place and meet all of us and find out all the different opportunities that exist in one organization. And like I said, maybe for the next 5 years, it's ITER who's provided the opportunities for the cryogenic systems, but then maybe the ESS will come or CERN will come for another 3 or 4 years. So we attract industry and we keep it in this big science market. So this is one of the big advantages we see in these type of events.
In terms of breakthrough fields in industry, we're speaking about the kind of new materials that can contain, when you have all this going on with the plasma, you need materials with special characteristics, yeah, to be able to contain it. And you speak about the superconducting magnets. Can you just list give us an idea of some of the real breakthrough technologies that are involved from industry side in building the reactor?
I mean, in all of the technologies, all of the range of technologies that are involved with ITER are maybe not at the breakthrough stage, but in most cases they have never been built before, at least the size and the complexity. So maybe the technology is not always new. For example, the superconducting technology, it existed before we came, but a magnet of the size and complexity of the ITER magnet had never been built before. So, in a sense, it is a breakthrough from that point of view, from the manufacturing point of view. We're talking superconducting magnets, we're talking cryogenic systems, we're talking tritium technology that would also come. We're talking some of the control and diagnostic systems that are extremely important. We're talking about remote handling and robotics, which will be used for the maintenance, inside maintenance of the ITER machine. Those same robotic systems can easily be used in space or on exploration to Mars or in other areas like this. So most of the technologies that we are using and we are making develop further, they can easily be taken up by other areas of work, by other industries or by other applications. Some of the superconducting technology is also used for the MRI machines that are used extensively in medicine, for the diagnostic systems in medicine. So there are many, many spins of the technologies that we help develop.
And this is also now people speak about knowledge-based economic growth and to provide jobs that are not based on cheap labor but high knowledge. And this partnership between the big science and the industries is involved in challenging industry to develop the most, to keep on developing new technologies. And then when new science comes along, then that enables the industries to make more high technology. It's like a symbiosis.
Yeah, absolutely. I mean, we have made our own, calculations, and it's true that all the money we pump into the European economy, and we're talking almost 8 billion euros from 2008 till the construction of ITER in 2025. So all this money goes, most of it, into very high technology. Although we have some civil engineering, clearly the buildings on the site, many of it go into manufacturing of high technology, and this generates a lot of employment, a lot of stable employment, and we have a lot of competitiveness and growth in the economy itself. For Europe, it's important. We have been a leader in fusion since the 60s, and we want to be able to maintain this leadership. And why not? When the time comes to start building commercial reactors around the world, we would like a European consortium to be there to be able to do that, or to get a part of the pie.
And just lastly, why is actually Søren Pind, the Danish minister, he started his speech by saying that this conference is like a peek into the future. What would you say to the citizens and the politicians who would watch this video about the importance of fusion as a way to the future?
Yeah. Well, I mean, we all know the difficulties we have today in relation to energy. First of all, our needs are growing. By 2050, our needs will have doubled as of today. On the same hand, we have amazing, very complicated problems with the environment. We need to stop CO2. We're killing the planet, so we need a new form of energy that will satisfy our needs, and we need an energy that is clean and sustainable. Renewable energies in the different forms, from solar to wind power, are great, and we are very happy that we are all developing, in each one in a corner. But I think we also need another type of energy, a base load form type of energy. We'll be able to provide our needs, tap in and get more if we need more. The wind may not blow on a particular day that we need more power, more energy. The sun may not shine, but fusion, you can put more fuel and you can produce more. And this type of energy is what we need. We hope to be able to provide it and have it for the ready for humankind like I said, in the 50s or 60s of this century.
But that's also dependent on the commitment of the politicians and the voters to invest money, and lots of money, and that the timetable is also dependent on the will.
Yeah. It's clear this is public money, at least for Europe. It's 100% public money. So we need to convince the public, we need to convince the representatives of the public that this is a good project, this is a good investment. It's worth it not only for the long-term effects of making fusion a reality, but also for the shorter terms. Like we said, putting all this money into the economy makes things better for the economy and for everybody. So that's why we're here. We're trying to convince people that this is the way to go and to continue to have our support. As far as Europe is concerned, we have the support of the EU guaranteed for the construction and operation of ITER, and obviously we will need to come with their plans, very clear plans, together with a budget and a timetable for the next generation. But one thing at a time, we're now trying to make ITER a success and exploit the magnificent research machine that ITER would be, and then we will take it from there.
Thank you very much, Doug.
You're welcome.